Switch between the laser endpoint and the optical endpoint with this button down here. So the system can handle use if you have a thing where you might want to use both the spectroscopy endpoint and the laser in the same recipe. That works, but you cannot see both the screens at the same time. But it will collect the data. Okay, but let's go through this PC up here. I'm just going to close everything and we can start from the beginning. Close everything. Normally everything will be running, but I want to show you how to start everything in case some other person has closed it. So there's 3 softwares we need here. We'll start with this one. So this is the view of the camera, so you can see where you are. Just pick this live video and press the play button. Now I'm unable to save the settings that I like the best in a way that it will automatically start with those settings. So when you open it up, it will have a quite poor resolution of the camera. But and I've not been able to convince it to change it by default. It will still work fine, but the resolution of the camera is not that great. But if you go to load parameters and just choose this parameter set, then it will improve the resolution. But I cannot save it to automatically do it. Okay, so this is showing the camera, and here is our laser spot. What you are seeing right now is the surface of the electrode, because there's no wafer inside yet. So it's not very exciting to do. What I'm not going to show you is how to focus and align the laser spot, because that can only be done by going in here, and you are not allowed to go in there. So I will not talk about it. The good news is, as long as your samples are relatively all the same thickness, within a few hundred micrometer, you do not need to focus the spot on every run. You only need to move it in X and Y, and that we can do from here, but you don't have to actually focus it.
So we can move the stage?
Yes, this I will show you now.
Okay.
But you cannot focus, you cannot move in Z, you can only move X and Y. So I'll show you how to move in X and Y. Because that you will need to do. So to move in X and Y, you need this one. Now we haven't given you some very advanced joystick software. So this is basically a direct link into the motors, XY motors. So it's not the easiest thing to work with. When you open it up, you just have to press this to locate the motors. It takes only a few seconds. And then it will find 2 motors here. One is X movement, one is Y movement. And you can set it to please work in micrometers, then your life will be easier. And you control them down here. If you use this one, it will just take a step. See, it just moves a step in that direction by this amount of distance. If you take this one, it will move continuously until you press the stop button. And that way you can move it around on the surface. So this is something you will in general have to do when you load your sample in, to move the spot to a correct place on your sample. Of course the other direction is the other motor, but it works the same way. You feel free to change these numbers, that's just what I put in. If you want to take shorter steps or slower movement, just change these.
So what is the resolution of movement?
I don't know, I think I can put 1 micron. Yeah, that works. Now it's really moving slowly. Yeah. Now, the size of the spot of the laser is something like 60 to 80 micrometer. So that means the area that you need to be able to hit on your sample needs to be at least bigger than that. I normally tell people, please make a box minimum 150 times 150 micrometer. You need to have a big enough box that you can put your laser in the box without being interfered by looking at masks or nanostructures or anything else. So this is a restriction on the use of the laser. You need to have a suitably large area where you can actually fit the laser. Which sometimes is not a problem, sometimes it's a problem. It depends on your layout, how easy that is to do. It's the reason why a lot of production facilities, they really hate the laser, because they don't have this anywhere on their layout. And
what is the spot size? Can you repeat?
Approximately 60 to 80 micrometer.
So it's very small.
some people say, oh, it's so big, and other people, oh, it's so small. Yeah, so it depends on your perspective. Yeah. But if you go to a chip fab or something that makes complicated devices, and you tell them directly in the middle of the wafer you must have a big empty space, they will laugh at you and say, no, no chance. It's the most valuable place on the wafer. Yeah. So a lot of production facilities, they really don't like that for this reason. But for research, it can be very good. Okay. So this is how to move the spot around. We will look at this again when we try to run a real sample test. But for now, we will just leave this alone. And then we'll open this thing, Edge Director. So Edge Director is what actually takes charge of the acquisition and treatment of the data. So it looks a little bit complicated. It turns out it's not that complicated. There are not that many options. So we'll go through it step by step, and we'll figure it out. There is a manual. I've given it to the KAUST team here. It's also on the desktop of this PC. There is a manual. If you have time, if you have interest, please read the manual. It will explain in much more detail than what I'm doing. But okay, so there's 5 pages here. This page will show you the data that's being acquired. This page will also show you the data that's being acquired, but this one will zoom to the last something seconds that we will specify. And this thing here is where we will set up the acquisition, not the acquisition, the treatment, data treatment parameters. So this is our algorithm for the endpoint. This thing here lets us model the predicted shape of the signal. And this thing here is a material library for what materials you can easily insert in the model. So we're gonna start with this part, and then we'll talk about this part, and then we'll run a real one, and we'll see what happens in this part. Okay. So this part is where we set up our algorithm. The system supports 5 endpoints. You can see there's 1, 2, 3, 4, 5 endpoints. So we talked about the different modes. You can look for a flat, you can look for a rise or a fall, or you can look for the period of the oscillation. And these things can be one individual endpoint. So if you have something that first has an oscillation, then it goes flat for a while, and after that it has a drop. This is conceivably possible. Quite rare to have something like that, but conceivably possible. It's possible. This you could program in the machine as to first have a loop when it goes flat, and then when it finds that, then change, okay, now I want to see when does it drop. So you can have 2 subsequent endpoints. In reality, it's quite rare that there is a demand for this, but the system supports it. Okay, but we'll talk about just one at a time. So the first thing we need to decide is which of these detectors we have to use. I will explain only the simplex, the model, and the kink, because the anomaly and the flip-flop is new in this version. I have not seen them before. I don't know what they will do. I looked in the manual and they don't explain it. So I have no idea what they do. So I have to contact the guys from Intellemetrics and say, can you send me a manual about what the hell these things do? I don't know. I don't know. If I get information from them, I will share it with the KAUST guys. Right now, I don't know what they do. Okay, so we'll start with the simplex. So the simplex is the case where you want to measure the edge rate and stop after a certain amount of nanometers. So we'll just explain these parameters in a moment. We start with these ones. So first of all, here is where you type in the wavelength of the laser. So that is 670. It does not autofill, you have to type it in. So if some other student changes it, you have to make sure that it's correct before you run your stuff. And there you type in the refractive index of your material. And then here you type in how many nanometers you want to etch. Or be careful with the units. It says micrometer here. Yeah. So 500 micrometers, that will take a while. Yeah. If you want to change the unit, right click, and it lets you change the unit. We'll change it to nanometers. But be careful with that. I made a mistake yesterday when I was testing it, because I had not noticed that it was micrometer.
Excuse me, this means the thickness?
So this is the thickness, this is the depth that you want to etch to.
Okay.
Not how much is remaining, how much you have removed. The top one here, where it says buffer size, this is the algorithmic detection. So this is how many data points in the past is the system looking at to to figure out if you are at a turning point or not. Yeah, so this is like a noise removal thing. Yeah, so you need to look a certain amount of data points in the past to confirm, yes, this is actually a turning point, either at the top or at the back, at the bottom. And this is something that needs to be a little bit adapted based on each individual process, because depending on the etch rate, this number can need to be different. So if the etch rate is very slow, it has to look at a relatively long history to make sure, yes, it's really turning. If the etch rate is really fast, it doesn't need to. It can detect only with a few steps. So this is something that you will quite often need to adapt a little bit based on each individual application. But I will show you something that the machine can do to help you with that. Okay. This thing measure from go, it just means start immediately, don't wait. And that's what we typically do. You can program in here a delay, but we typically don't do
So
it.
last time you told
Yeah.
that if we add delay over here,
Yes.
so there would be between two layers we can detect something, you told, right?
Yeah.
So this is that the place where we add delay?
No. Normally I do it with this one.
Okay, hold. Okay.
So this one functionally is the same. Yeah. So this hold off is just ignore the data for a certain amount of time. So I usually use this one. I don't use this one. I usually use this one. The top one here where it says filter cutoff, this is a smoothing procedure. So it always smooths the raw data that it picks up from the laser. And this is a filtering algorithm that does this. Basically, essentially the lower this number is, the more aggressive it's smoothing the data. And I'll show you, after we etch the sample, I'll show you the effect of this smoothing. Then there's this one, this is an overage. So basically after it has determined that we are at endpoint, you can choose give me some extra time. Now if you're using the simplex, normally you don't use the overage. Because if I have set it, I want to stop when we are at 500 nanometers. If I have overage set, it will reach 500 nanometers and then it will do more. Yeah? That's kind of not the point. Yeah? The point was to stop at 500. Yeah? So when we use the simplex, we typically don't use the overage. This timeout, don't worry about it. Just forget it exists. Okay. So the simplex we use in the case where we want to measure the etch rate and stop after a certain amount of time. The other use case, we will use what's called a kink. So we change to the one that's called kink. Now I have 3 buttons here: slope, sensitivity, and window size. So slope is the slope that it should search for. So if I write 0, it means search for flat. If I write something positive, it means search for rise. If I write something negative, it means search for drop. Yeah. Now it's very hard to understand the unit of this because it's not specified. But just as an initial guideline, if I'm looking for something rising, I write 0.1. If I look for something falling, I write minus 0.1. And if I look for something flat, I write 0. Again, this is those plus 0.1 and minus 0.1. That's something that could be need to adapt it for each individual application. But this is just the point where I would start. Sensitivity means how close should the real data match the demand. And again, it doesn't tell you anything about units. Even the manual doesn't explain the algorithm it's using. But the way it works, let's hope I can say this correctly. Correct me if I say it wrong. So if you write a higher number here, it's less sensitive to the data. So if you write a higher number in sensitivity, it doesn't have to be so flat. It can still wobble a little bit. If you write a very low number in sensitivity, it must be really perfectly flat before it detects it. But it doesn't explain what is the difference between 5 and 1 and 10 really in the mathematics. It doesn't tell you. The window size is again how far in the past, how many data points in the past needs to match the demand. Yeah, so if this is very high, it needs to be flat for a very long time, or relatively long time. Where if this is really small, it can be flat even for a short time and it detects. And again, this is something that needs to be adapted based on each individual process. Now, it has the option over here, if you enable this, follow TPs. TPs is turning points. then it will do at the same time. So these are all the options we had in the simplex. Yeah, they are repeated here. So this gives you the option that while it's searching for the going flat, it will also measure the edge rate. But if you enable this, you can enable that, it's fine. It's only for information. The actual stopping of the process is controlled by this. This part is only for information. But sometimes it's interesting to see. Okay. With the kink, we have still the filter cutoff and the hold off and the overedge. They do exactly the same as I explained before. The difference is that if we are using the kink, we often have some overedge. And there can be two reasons to have an overedge. First reason is if you have a large sample or a complete wafer, the point where the laser is pointing is not necessarily representative of the whole wafer. So there will be some variation in edge rate across the wafer. So maybe the outside of the wafer needs a little bit more time to finish even though the inside is already finished. So then we will give some overedge to make sure the whole wafer is finished. The second reason is, remember the laser needs the big box to point at. So if you have some nanostructures on your sample or narrow dimension structures, they are slower than the big dimension structures. So you could also need some overedge after the laser is detected to make sure the narrow stuff is also completely finished. We would usually use between 5 and 10% as the overedge value. But in some cases you might need a little bit more. But between 5 and 10% is common. Okay, the last one that I will explain is the model. To explain the model, we first have to talk about the model. So let's park this and we go over here. So the system allows you to build a model of the structure. I'm just going to delete everything that's here right now, because that was things we were playing with before. So it allows you to build a representation of your layer structure, and this can be used to give a prediction of what signal you can expect. And it can also be used to feed back into the actual stopping of the process. We'll explain these two parts separately. So let's build a simple model and just...
Yeah. So this mode is mostly if I want to etch, for example, layers not completely.
Yes, it's mostly used if the two other options I explained first are not applicable. So if you cannot use the simple simplex and you cannot use the simple kink, but you have more complicated stuff. So it's usually if you have like DBR gratings with many different gas, L-gas, or if you have indium stuff with all kinds of in-gas and random stuff, where you have many different layers, then the simple detectors cannot cut it, because the refractive index is constantly changing. So yes, you have an oscillating signal, but it's not always the refractive index, same refractive index. So the amplitude and the period is constantly changing. Then the simple simplex cannot predict the edge rate. In that case, you use the model. Or if you have that picture I showed you with metals and oxides and everything all jumbled up, also the simple detectors cannot help you, but the model can help you.
So I have one question. So what's the main difference between the first simplex and the second one? I think both of the mechanism is to see whether the slope is flat after you finish.
No. The simplex, in the simplex, you stop before it gets to the flat part.
Before?
Yes.
Oh, right.
Yes.
So we type the edge depth we want to.
Yes.
And
Yes.
we can stop right at this.
Yes.
I see.
Yes. Okay. Let's make something simple here. So you can add a layer by pressing the button here. Add layer above cursor, and it adds a layer. Now it's a little bit clunky to work with this editor. You can type in everything yourself. So the name of the layer, the refractive index, and the K factor, and also the thickness. Or you can load them from the library. But to load them from the library, you have to double click, and then the library shows up, and you can try and find what you are looking for. It's a little bit clunky, but it's the only way. So we're just gonna do something simple and put some silicon oxide on top of silicon. So we'll find silicon oxide here. So if you do it this way, it will load in the refractive index from the library. If you just type in, you have to type in everything. And let's say we give it 500 nanometers, because that happens to be the sample we have available. So when you have typed in your layer structure here, if you press this button here, it will create the expected response from etching this layer. So you can see we get it will not show the substrate. Yeah, so it does not actually show that it goes flat, because it doesn't show the etching into the substrate. But you can imagine from here it will just continue flat. So you can see that we have a little bit more than 2 periods here of the oscillation. And if you remember the calculation, 670 divided by 2 times the refractive index. The refractive index of silicon oxide is 1.5. So 670 divided by 3 is 220 something. And we have a 500 nanometer layer, so 220 and then 220 again, and then a little bit more. We reach 500, so it matches. Now if you have something more complicated, so let's add some more stuff. Let's say you have some silicon nitride on top. This one. Let's say you have a 300 nanometer silicon nitride on top, and we model this. You can see now we have 2 different periods. Now you have to be very careful with the model when you have multi-layer materials, because the model will always assume that every layer is etching at the same rate. So the x-axis here is not time, it's depth. Yeah. So in reality, the etch rate of the different layers is not guaranteed to be the same. That depends on your process and your layers. Sometimes it's close, sometimes it's completely different. And if the etch rates are not the same, then the period here will extract or contract, expand or contract depending on the relative etch rate. And that's something the model cannot guess. Yeah? So don't put too much faith in the model if you don't know the relative etch rates. You have to think about it. It's often the case that the model is not good enough. You have to just try and etch it and see how it looks. And sometimes it's good enough. So I will show you the option to import directly the model into here, and then I will tell you that you probably will never do it. But I will first show you how it's done. So you can save this model here. I press the save button. Now, before I do this, one thing to be very careful with: if you save this button here, it doesn't save the result of the model, it saves the definition of the model. So it saves the table here. If you want to save the actual graph, then you need to do it in here and then press this save button. They don't do the same thing. So if I save this one, you can see I did it already when I was training the other guys yesterday, but do it here. Actually we'll make a new one, because this was only the oxide. I'll just save it on the test. Now we can actually import that over here. So if I choose in here the model, then there's a button here that allows me to open the model. We can now open our test here. Now we get exactly the same curve over here. Now what we can do is, I can tell it I want to finish at 450 nanometers. Now get a red, again it's micrometer. Nanometers please. And I get a red line here. So that's 400 nanometers from the very top of the sample. Now, and I can move this around if I want to. So if I would use it this way, then it will, when it runs the real acquisition, it will again, one thing that's very important to understand is the only thing the algorithm will detect is the turning points. So it finds a turning point, then it finds the second turning point, and then it assumes the next one will be this one, the next one will be this one, then it will be this one, and then I need a certain amount of seconds extra, then I should stop. It does not check the slope here, it does not check the amplitude here. It only checks how many turning points have I reached, and then it knows a certain amount of seconds after this one I should stop. That's the only thing it will do. Yeah. And that's a little bit of limitation in the application of the model. The advantage of the model is, now I just did a model here, and I put that in here. You can just do a test etch So if you do one etch of a sample, you have to waste one sample. But you etch one sample, you just acquire the data, then you go to the deck tag or the SEM, and you measure how deep did you etch. And you can save the run data as a model and tell it, after this amount of signal, I had etched 1.4 microns. And then you can import that data in here. So instead of having the model data, you have real data that you know how deep it was. And then you can do the same thing. You can point somewhere earlier. Let's say you had etched 1.4, but you really wanted to have stopped at 1. So you load that data in, you say that was 1.4, but actually I want it here. And then the next time it will stop there. So that is what we do if we have something very complicated, which I'm not going to spend time modeling here. Actually, we did prepare something very complicated. So we were just playing around, so we deposited a super stupid stack. but in this case, the model looked like this. So that's super complicated. But if I could put that in here, and then I could tell it to stop here. And this would work because it will find this turning point, and then it will find this turning point, then it will find this turning point, then it will stop here. So this is how you get around the limitations of the simplified algorithms. You either make a model that you know you can trust, which is relatively rare, because typically the relative etch rates screw it up. Yep. Or you etch one sample, collect a data set that you know how deep it was, and then you use that to put in, okay, I want to stop this far before. Yeah. But that's something you will need to practice and play around with until you get comfortable with it. Yeah, it's so dependent on the individual application. That's not something I can easily teach you. So you will need to practice with it. What we're going to do now is we're going to do something simple. Just to show you the principles. So we're going to do the kink detector to etch this silicon oxide piece. So what I'm going to do is I'm going to open silicon test that we have prepared before. So here I have set some numbers that I expect will work. And we're going to etch this on the sample that's in there. But before we start the process, I'm just going to show you how to set up the recipe here to connect to this. Okay.
Can I ask a question?
Yes?
What's the sampling rate of this detector?
I didn't tell you. By default, it is 5 Hertz. So you get 5 data points per second. You can change that. It is up here. You can change it here. I do not know what the maximum is. I'm not sure. We generally just put it at 5 Hertz and forget about it. It's good for pretty much everything. 5 Hertz is okay. But it is possible to change it here if you really want to. Just to be clear, it's important if you change it, because these numbers here, the window size and the buffer size, they count data points, not seconds. So if your sampling rate is 5 Hertz and you put here 5 as the buffer size, that's 1 second in the past. Yeah. But if you double the sampling rate, then this is half the time. Yeah. So if you modify your sampling rate, you might also need to modify these to get a similar result. That's something to just keep in your mind. The reason this is alarming is because I restarted this software. If this Edge director is closed, then this software will start complaining, say I cannot communicate. But it should resolve itself, I hope. Yes, it resolves itself. Okay, so we go to the recipes. So we have a recipe in here. There's only 2 things you need to modify to be able to talk to this. Well, there's one thing you must do, and there's another thing I recommend you to do. I'll show you both. The thing you must do is there is a device in the recipe called laser endpoint. So that needs to be included in the recipe, and you just turn it on. So you choose here. You have 2 options. Don't use the end recipe. You can choose monitor, or you can choose end step. If you choose monitor, then even if this thing decides this is the end point and sends the command, now you should stop the plasma, this thing will ignore it and just continue anyway. So this is what you can use if you're not sure this is going to work and you don't want it to automatically stop the plasma. And you can put it on monitor. If you put it on end step, then when this thing decides, okay, now it's finished, I should stop, it sends the signal and the plasma will stop. Yeah, so this is what we use if we are doing fully automated processing. Here I will put it on end step because we expect it will work. Then I have to write in here the script that it should use. And what you need to type in here is what you have saved in this box. So this now is SiO2 test. You don't include the .edp, just the first part, SiO2 test. So this much must match exactly what you write here. Don't make any spelling errors. It must be exactly correct. Yeah. Okay, so this is what you must do. The enabling of the endpoint must be in the same process phase where the power is turned on. Yeah. So if you try and enable this in a phase where there is no power, it will not work. It cannot monitor when there is no plasma. It will not work. That's one thing. The other thing is if you have two phases after each other, both of them with plasma on. So if, for example, you have a strike and then a main, you must put the laser only in the main, not in the strike. Otherwise, it probably will not work. There's a chance it will work, but I don't guarantee it. So in general, put the laser on only in the main edge part of the recipe. Okay, the second thing that I recommend you to do, so you need a certain amount of time after the wafer has been loaded in before the plasma starts, so you have time to move the spot around to find where it needs to go. And in the standard creation of the recipes, there is no time. As soon as the wafer is loaded in, it begins the plasma. So you have no time to put the laser spot. So what I have done in this recipe is I have added delay time. There's a step even before where I just let it sit for 3 minutes doing nothing. And this gives me 3 minutes time to move the laser spot where I want it to be. And then when I am happy, it doesn't necessarily take me 3 minutes. It might take me 30 seconds. But when I'm happy, I can just press the skip button and say, okay, now go move forward in the recipe. So, in addition to that, in this step, I turn the helium on. So when the helium is turned on, the helium backside cooling, the wafer flexes a little bit. Yeah, not a lot, but a little bit. And if you have a very sensitive positioning of the spot, you're really trying to hit a very small hole, this flex can be enough that it doesn't align anymore. So if you adjust the laser before you turn the helium on, and then say, okay, now it's perfect, and you start the recipe, then the helium comes on, and you have to panic and do it again. Yeah, so that's why I put the helium on here, so you adjust the laser at the same conditions as the real plasma. So I recommend to put this in. This is not required, but it will really help you out if you have a step like this. Okay, so we're going to run this recipe, and hopefully you will see appearing on the screen here this oscillation curve where it does 2 periods and then it goes flat and then it will stop the plasma. That's the plan. So let's see if it works. It worked yesterday, so I hope it works again today. So I just call this lab training. So if we look at the camera, then we will see the wafer arrive. We'll follow the recipe. Okay. Now this piece we have no pattern. It's just completely blank. And sometimes it can be hard to see if you're on your sample or if you're on the carrier wafer. So we'll try and figure that out in a moment. I think we are on the sample. Right now everything is defocused. It's because the transfer has not been completed yet. So the wafer is still sitting high above the electrode. So in a few seconds it should come down and everything will be in focus. There we go. Now, you could begin already now to move things around, but I recommend you to wait until you see that it's in the delay step. Which it is now. So now we have time where we can move things around. So I'm sure here I can see this is the edge of the sample, and this is the carrier wafer. It's very ugly. This is my previous sample. Please try and avoid putting your laser spot. First of all, of course, it should not be on a big piece of dirt like this. That will screw you up. Try not to be too close to the edge of your small piece. You can get all kinds of edge effects. Try and avoid that if you can. Put the laser somewhere closer to the middle of your sample. You will in general get more reliable results. But yeah, just find some nice place, and when you are happy, then you can get out of this. And in here you just press the skip. You can press skip here, or you can press skip here. They do the same. Skip here. Then we get into the plasma. So now stabilizing the gases, and when the plasma turns on, it will begin here, hopefully. There we go. So now this has begun. So you will notice I have enabled this option that it will measure the edge rate also, even though it's looking for the slope. And you will notice over here, it will tell you once it has determined the edge rate, you will be able to follow it here. It needs to find one maximum and one minimum before something will arrive here. So if it has not found at least half a period, it does not know the calculation. What you will notice, there is a red dot here. Red dot means here I have determined it's the top of a period. When it gets to the bottom, you will see a blue dot. So by noticing these dots, you can confirm that the detector is detecting everything correctly. In a moment we'll see a blue dot. There we go. That's a blue dot. So now we get numbers here. So we get a measurement of the edge rate and also the measurement of the total depth we have reached. Really cool. Now the accuracy of this depends completely on how accurate do you know the refractive index. Sometimes you know it really well, sometimes you might not. If you don't, then this will be less precise. But hopefully when this says around 500 nanometers will correspond to the time when we get a flat signal. Because here we are quite sure we know everything correctly. Now, if you are watching this and you realize, oh, I screwed something up, and actually I should stop now, press this button, force cut. If you press this force cut, it will send immediately the signal. Actually it would treat it as if it was endpoint, then it would do the overage, and then it will stop the process. So if you think you have missed the endpoint and you really should stop around now, press this button. If you can of course press this button to stop the process from here. If you do that, it will screw up the communication between these two. And you have to restart the software to get it working again. Yeah. So try to avoid that. If you want to abort a recipe you're running with this endpoint, please use this button, not this button. You can do it, but if you do it, you have to restart this edge director afterwards. Otherwise, it will not work for the next guy. And it's not easy to see that it's screwed up. There's no big error message here. It's quite hard to recognize. So please try and remember, if you want to abort, use this one. Okay, so now we have reached 500 nanometers. And we should see a green dot in a moment. So we get a green dot there. That means it has now detected, yes, this is the flat part. And then it does I have set here 20 seconds overage. That's really long for this process, longer than you normally would use. But I've chosen this just to show you in more clarity what's happening. So we will get it in there. We get a gray dot. Gray dot means it has now commanded the process to stop. And indeed we can see the plasma has now been turned off. And it has completed the process. So everything worked exactly like it's supposed to work. Now there's several things I want to show you before we wrap up on how to look at the data. The first thing is, you can see here there is a little blue dot. And this is because the detection algorithm of the turning points has a hard time when the signal is actually flat. It's very hard to accurately detect these because it continues looking for turning points. And And when the data is almost flat, even a little bit noise, it thinks is a oscillation. So after this point, the value you see here goes completely crazy. You cannot trust it anymore because it thinks this one was already all the way back down again. So you can see now it says I actually edged 700, but it's wrong. It's because after it goes flat, you cannot trust this edge rate measurement anymore. Just be aware of that. The second thing I want to show you is the smoothing. So in this graph here, I can click this button up here, show raw data. It will show me some white line also. The white line is the raw data that it's measuring from the laser, and the turquoise bluish line is the actual process data. So this is the smoothing that I explained before. So you can see there is a delay. If I can click here, I can determine how much time back in the past I'm seeing in this screen. So you can see the white turning and the blue turning. There is a delay between these two. And this is because of the smoothing. So if you're very, very sensitive to the time, then sometimes this delay is not good enough, yeah? Because it means you are actually stopping a few seconds later than you should be stopping. Yeah? But if you're really smoothing a lot, it could be more than 2 seconds. It could be 5 seconds or 10 seconds conceivably. So if you are very, very sensitive to stopping exactly on the right spot, then too much smoothing can give you an error that you don't want. Yeah? Now you can fix that by smoothing less aggressively. Yeah, I'll show you. So one function, the function that I will show you that's super handy is you can repeat with different settings without running a new wafer. So you can basically change the settings and rerun it on the same run data. So you can check the effects of changing these values without having to use another sample. So if I just go down here and I change this filter cutoff, instead of 0.1, I write 1. I save it. Actually, no, let's make a new one. Test. Just call it test. If I press this button here, it looks like a old telephone. I don't know why it looks like that, but if it does. It will basically rerun this on the same raw data that I had here. So if I press it, you can see now the white line and the blue line are directly on top of each other. So I basically removed the delay. Now that works great in this data because it's super easy data. There's a high amplitude intensity, so there's very little noise. So I didn't really need to do any smoothing. But sometimes you change this and the raw data is too noisy. So it will not be able to accurately detect the top and the bottom. But again, this depends on the individual situation you're in. Let's change it to somewhere in between so it's a little easier to see. Again, now you can see just a little bit off. So you can modify this to change the smoothing. Now let's show you. Now I practiced, so I set these sensitivity and window size so that I knew this process was going to work because I already did the practice. But let's show you how it can look if you give bad values for these. So let's try and decrease the window size. If I set a very low window size, it means it's looking less time into the past to figure out if it's flat or not. So let's see what happens if I run this. You can see now I get a green dot here. Why do I get a green dot here? It means if you zoom in right around the top of a bending, it looks flat, right? Right at the peak of an oscillation, it looks flat. So if I don't look far enough into the past, it thinks the top here is actually flat. Yeah? Then it fails, because this will have stopped the process here. This is a failure. And that's what can go wrong if your edge rate is slow. Yeah, so if I had it like 14 like I had before, but I used a process that had a lower edge rate, I could run into the same problem, that it would think the top of an oscillation is actually a flat surface. And that's something you have to optimize then process by process, especially this value. Now the window size and the sensitivity, they work together here. So remember the sensitivity is how flat does it need to be. Yeah? So this you could also change to prevent this. And it's not always obvious what should I choose. Should I change the sensitivity or should I change the window size? It's not always obvious what is the best choice. So that is something that again needs to be practiced on an individual application to figure out what works the best. Yeah. So in general for lasers, endpointing is hard to guess correctly every setting the first time. If you have something completely new, it's very hard to make a good guess at what numbers you should put in here. It quite often goes wrong. So it's very often the case that you need to waste one sample. So etch one sample, just etch through the whole thing, and then use this reprocess function to figure out what settings you should set. And then the next wafer is going to work. But it's very often the case you need to waste the first one. As you get more experience, if you're doing something that's very similar to something you've done before, then you can get better at making a good guess the first time. Yeah. But at the beginning, it will probably go wrong the first time. But the second time it will go good. Yeah. Again, you can just forget about this and just do the manual stuff. If you say, this is too complicated, I don't want to work with it, I just want to look at the graph and press this button every time, I don't have a problem with that. You are free to do that. You will not get any complaints from anybody if that's what you want to do. So pick what works best for you and go with that. Okay, is there anything else I need to train you on? Just the saving. So the system is set to save all the data automatically. If anybody disables that, kill them. But I'll just show you where it is. If you go up here on the run data, it's set autosave. Please never remove this autosave. Just like the spectroscopy OES, this software does not know what name the wafer is. So it does not save anything with a useful file name. I put a shortcut here to the location where it saves the data. So it will just save a file that's just named run and then the time when it was done. That's all you get. But this will let you locate a day or a week or a month later to find the right data set if you want to look at it again. If you want to really help yourself out, then as soon as you have finished the data, go in and rename the file or copy it immediately off to your own PC so you have it separately. Or just leave it here, know that you can find it again. Hopefully nobody will ever delete it. I'm afraid this software is not available as an offline copy. So if you need to do some offline data treatment, you want to look at the data, you have to be in here to look at it. It's not available as a separate software. But yeah, I think that's it.